Hi, this is Tony and Ian from Tektronix.
And today we're going to show you a video on an oscilloscope, the basics of it and its main features.
We're going to do that by starting with something that brings back a lot of fond memories for electrical engineers, a simple RC circuit from the first day of undergrad electrical engineering class. That's going to serve as our springboard for moving on to how to operate an oscilloscope. So at its heart, an oscilloscope is a device for seeing how the voltage of a signal varies over time. For example, imagine a simple RC circuit with a battery, a capacitor, and a resistor.
And technically it's not a circuit yet, right?
Right, exactly. We haven't taken the last step of connecting the battery yet. First, we're going to add one more piece to the puzzle. We're going to connect an oscilloscope probe across the leads of the capacitor. Now, when we connect the battery and complete the circuit, you would expect the voltage to start at 0 volts and then rise as the capacitor is charged until it reaches 1.5 volts. And if you have a correctly configured oscilloscope connected, that's exactly what you would see. And it would look something like this. You can see how it starts at 0 and goes up to 1.5 volts. Now, this signal is pretty stable. Real-world signals change a lot over time, and that's where knowing your way around the front panel of the scope really comes in handy.
So we'll take a look at a scope with a repeating signal.
Right, so here's a much more realistic signal, a sine wave. In fact, if you watch this sine wave long enough, maybe you'll see some glitches in it or some inconsistencies, and that's what, as an embedded designer, you're trying to zero in on. So this particular scope can display up to 4 analog channels from different inputs, and each channel has its own independent set of vertical controls. That means each waveform can be positioned independently of the others on the screen. And the two most important vertical controls are the vertical position and the vertical scale. So the vertical position moves the waveform up and down the screen, and the vertical scale expands or compresses the waveform vertically. Vertical scale is expressed in volts per division. So this particular model scope has 8 vertical divisions. Most of our scopes have 10. But if you have 8, and if you happen to have it set to 5 volts per division, you could fit a 40 volt peak-to-peak sine wave on screen.
Can we take a look at that on the oscilloscope?
Good idea. Let's do that. So we've got a nice stable square wave on the screen, and I'm going to reach for the vertical controls that go with the channel we've got connected, channel 1. And as I move the vertical position down, you can see the waveform moving down on the screen. And if I move it back up, you can see the waveform moving back up. So this is a very continuous knob. You can position the waveform exactly where you want it. The vertical scale is more granular. It moves in clicks. As I move the vertical scale 1 click larger, the waveform gets smaller on screen. And if I move the vertical scale 1 click smaller, the waveform gets larger on screen.
Oh, that's great. Can we move and look and see what the horizontal controls do?
Yes. So all of the input channels share one common set of horizontal scale parameters. That means as you adjust the horizontal controls, all of the waveforms will move together on the screen. So the two most important horizontal controls are the horizontal position and the horizontal scale. So as you move the horizontal position, the trigger indicator moves left or right, and that causes all of the waveforms on the screen to move left or right together. And as you adjust the horizontal scale, that causes all the waveforms on screen to expand or contract horizontally. And horizontal scale is expressed in seconds per division. So if you have 10 horizontal divisions available on your screen and you have your scope set to 1 second per division, that means you can fit 10 seconds worth of data on the screen.
Oh, that's great. That's really similar to the vertical.
Exactly. Just a different...
Can you see down on the screen also?
Yes. So now I've got my hand on the horizontal position knob, and as I move it to the left, you'll see the waveform very slowly moves to the left, and the trigger indicator, which we'll talk about in a moment, also moves to the left, and I can move everything to the right as well. Now, like the vertical position knob, that's a very fine-tuned style of knob. The scale moves in clicks like the vertical scale does. So as I click it one direction or another, the waveform expands or contracts horizontally.
And now for the last set of controls, the trigger.
Yes.
Right?
So these take a little more explanation. Modern scopes have really sophisticated triggering systems. We're just going to talk about the bread and butter of triggering today, rising edge trigger. The rising edge trigger, you care mainly about the trigger level. The trigger level is the voltage that your signal has to cross through for the scope to consider it time to update the display. And with a rising edge trigger, you want your trigger level to be somewhere between the top and bottom of your waveform. And the reason it's important to set that correctly is without triggering, your scope just updates its data at arbitrary times, and your signal is repeating at arbitrary times, and those probably won't line up. So, for example, imagine that your signal looks like this, and that's what it looked like the first time the scope happened to update, and then the next time it was time for the scope to update, it happened to catch the signal a little earlier. So it looked like that. And then another time it updated, it happened to catch it at a completely opposite time, and it looked like that. And so you get this chaotic, unfocused display.
Which isn't too helpful, right?
It's not too helpful when you're trying to zoom in on what's going wrong in the circuit you're designing. So instead, what you'd like is to be able to start the waveform at some particular point, and then the next time that it's time to update the display, you'd like it to update at exactly the same point on the signal, so you get a much more coherent display.
Yeah, that's great. Can we see that on the scope here?
Definitely. So right now we've got a triggered display, but I'm going to move the trigger level way out of range, and after a few seconds the scope has gone to an untriggered mode, and it says auto here in the corner as a clue that there's something going on with your trigger setup. And as you can see, the waveform is just flickering all over the screen. But as we bring the trigger level back down, we can see immediately the waveform stabilizes. So whenever it's time for the scope to update, it waits until the voltage crosses through this level, and then it marks that point with the trigger indicator. It says this is the start of the signal, and it updates. And notice it's also able to display a little extra data before the start of the signal. How it does that is a discussion for another day. So we've really just scratched the surface of what an oscilloscope can do. We'd love to do more videos like this one, so if you have a specific topic you'd like us to cover, take a look below this video or contact us on Twitter @Tektronics.
And head right here to tech.com/learning, and there's a lot of resources there. Cheers.
Cheers.